like to run some tests on things that we have seen yesterday. So the idea is that given a document, an HTML page, we will try to download it, then separate its tokens, so we tokenize it, and then we try to apply a stemmer to it, so that we get the single stems that compose it. The toolkit that we're going to use in Python is NLTK, which means Natural Language Toolkit. And it's a library that contains many functions to work with all issues that arise with natural language processing. And in particular, we are considering the basic issues. So given some document, take the words out of it. Unfortunately, this toolkit, I discovered it this morning, is not installed on these computers. So I will ask you to do some preliminary steps in order to have it on your machines. And so the best thing, I suppose, is you just follow what I do now. So first, create a directory, maybe an RTK test, or something like that, so that everything we do will be inside that directory. And of course, go inside, so that you should be in the NLTK test directory. Next, we need to create a couple of soft links to my installation of NLTK on my home directory in these machines. So you should be able to do this. You make a soft link, ln space -s space. Let's try this. Tilde. The tilde character is to obtain this, you have to press Alt, graphics, and the key with the accented I and the caret. Okay, so this should give my home directory. Just to be sure, write it completely and then press. In fact, it doesn't work. Okay. Sorry. Okay, better not use the tilde at all, but okay, so the folder, the directory that you have to link is /home /mauro.brunato /pyaml 3.09. You just have to write the first pi, uppercase P and lowercase I, and then press tab, the tab key. Build, okay. So you must create a soft link of this folder in the current directory. Right. Sorry, I need to make some cleanup. Okay, that works. So, if you make a listing of the directory, you should find the YML. Then the second directory that we have to link is home. Now Brunato. Okay, the same home, Mauro Brunato, and LTK-2.0 and so on, then follow down. So now, if you look at your folder, you should have these two soft links, NLTK and YAML. As soon as you all confirm that you have it, we can proceed. Of course, you have to do it on the lab computers because you need to have access to the same file system as I have.
I think we've got permission denied.
What comment?
I can get just
So if you write, okay, so I need to change the permissions in my folder. Okay, try now. Now an LTK dash. So you had the same problem before with YAML, I think. Okay. Yes. You need to delete some files. I don't know, sorry. Make
maybe you can work together on her account or
All of these do not.
okay, then you probably have to try to delete something. Let's see. Yes, so if you get this, that's fine.
If you have your computer and you want to install it, okay, you have all instructions. Okay, so the home page is nltk.org. Then on the sidebar, you find download and you have this link, install the data. If you want to install it on your machine. No, not install the data, sorry, the one above. For the latest download instructions, please visit this at GitHub. You find the Unix instructions and below instructions for Windows. But I think that it's faster for now if you just link to my home. Once you have done it, we can test if everything works. Just enter the Python shell and try to import an LTK. In fact, I have problems. Oh yes, I was not in that directory. So from within the directory and LTK test where you have created those links, launch the Python shell and import the LTK. Okay, it should not give error messages. Something, and then press start again. Okay, left in the folder. Ok, ci sono altri permessi di accesso, allora devo... qualche permesso di lettura meno di quello che dovrebbe, adesso vedo.
Sugli Android va comunque.
Ah, quello va.
Veramente ho sbagliato a scrivere il percorso di
Ah, però non dovrebbe segnalare se il link è... Ma comunque verifico in ogni caso. Sempre. Va?
Sì, avevo sbagliato lì.
Ah, d'accordo. Vabbè, in ogni caso io ho aggiunto permessi di tutti i generi, probabilmente potete sfasciarmi la directory se volete. Adesso dovrebbe. Ok, quindi l'import funziona? Sì. Okay. Now, okay, how many people have the system working?
It's
Does it work? No.
very machine.
So,
So very machine.
let's see.
Ok, try to build the command there.
Or
Yeah, try it directly from here. Okay, anyone else having problems? Okay, anybody else? Okay, now, I suggest you do this to follow the rest of our work. So go to an LTK test, open an editor, gedit on some empty file, test.py. Okay, so here we will write the code. And I suggest that you also open another terminal where you launch a Python shell and import an LTK. So the idea is that we will make some experiments on the shell, so we see how commands work. And when we find some useful commands, we collect them on the Python file so that we have a program that we can re-execute at will. So, just to give you an idea of what we can do with this library, suppose that we have a string, let's say some text, okay, so just define a string with some English words. Okay, so for example, we can use a method of the unedit package. Word tool. Sorry. That applies to a string and provides as a result the sequence of tokens that compose our string. Okay, so let's say that this so we can take the variable text and assign the result of its tokenization to another variable, let's call it words. So words is this list of words. Of course, we can also take the words and make everything lowercase. Sorry. Okay, so lower cannot be applied to a list. So I have to map function lower on to a list. No. So again, create okay, this should work. Okay, I don't know if you are familiar with this syntax, but this is called list comprehension, and it means okay, if words is a list, then build a new list applying the function lower, the method lower, to all elements in the list. This is a list of strings, so it can work. And we can assign this to maybe, let's call it L words, okay, lowercase words. Now, so here we have a list of words that are contained in our initial string. Okay, so we had the initial string, which was, sorry, text, which was this one. We have separated it into words and then converted all words in lowercase. If you want, we can write the relevant comments in the Python file. So we import an LTK. We create some phrase in English. we tokenize it. And so if you just write this, maybe okay, I don't know how familiar you are with the Unix syntax. The first line says that the following is a file that can be processed by this program, by USR being Python. So everything else is a sequence of Python commands. If you go to your NLTK test folder, you can change to executable. So you can raise the executable flag to the program test.py. So that you can execute simply by writing no. Why not? Sorry, it was test. Okay, so we have declared. So we import the package, we declare a string, we tokenize the string, we convert all tokens to lowercase letters, and then we print the resulting list. Now, okay, is it okay up to now? Or do you need time? Okay, so once you have your Python file, you can just execute it either by writing Python test.py, or you can make the file executable with this command, chmod plus x and so on. And then you can also directly execute it by shell this way. Anyway, it is a Python script, so you can just write Python and then the name of the file to be executed. Okay, does it work? Okay, now, you see, the result that we get is just this sequence of tokens. Now, I would like to use a stemmer. Okay, as I said yesterday, stemmers are programs that remove the variable part of the word and only leave the stem, so the radix of the word. The idea is that words like, well, here is not. So if you take, I don't know, the word work and the word working, they should both be collapsed to the same word. Work, no matter the variable part. Now, let's go back to the Python shell. We can create a stemmer by, okay, we can create it. Let's call it st. So a stemmer is an object. So let's try this. Okay, there are many stemming algorithms. Okay, some of them only work for the English language or a particular language. There are some other algorithms that are more generic. Of course, a stemming algorithm is strongly dependent on the language. Of course, the same word endings that work in English, in, and so on, they won't work in other languages. So in general, a stemmer must be language aware. You must know what language you're working on. This stemmer should work for English. Once we have this stemmer, we can try to apply it to our set of lowercase words. So we can create a new list by calling the stem method of st on all words in well, okay. As you see, the only thing that this timer has done actually has been removing an S from this. So I'm actually not sure that it works as it should. Okay, anyway. Maybe we can later experiment with other kinds of stammers. So, once you have seen that it actually works, you can take, so we can assign, for example, to S words, so to stems, this list of stems. Okay, so stems contain the stems of the words of our string. Now let's take these comments and move them to our editor. So that finally, if you execute the Python script, you should get this list of supposing stems, of presumed stems. Okay. Now, in particular, we are interested in the set of words that appear in our string, in our document. So, what we actually want is to have, well, first, we only want to keep those words. Say, for example, we are not interested in this dot here, this point. So we can remove it, for example, by building another list. I don't know, filter the stems by filtering our list of stems by only keeping things that start with a letter. Let me try if this works. Here. Oh, sorry. Okay, so okay. So filter is a function that applies the first argument as a function to every item of the second argument as a list, and only keeps those elements of the list that for which this function is true. So this function only says that the first character of the string must be a lowercase letter. So by applying it to our list of stems, we actually remove everything that does not start with a letter, in particular punctuation marks. And finally, okay, we have this list of filter stems. We can sort it. So that we get a sorted list of terms, of stems that belong to our initial phrase. So let's say I want to end up with a list of sorted stems by applying the sorted function to my list of filtered stems. And finally, I want to print this list of sorted stems. So I just want to try if this works. Here. Okay. And English is text. Okay. So you should end up with a program that provides this list of words. And the program should be like this. Okay, now, does everything work? Okay. Okay, now, let's do something more interesting. First, I would like to collect all of these inside a function that we can call more than once on different phrases. So what I suggest is, okay, take the stemmer creation, and bring it up. Okay, so we can generate a stemmer once and for all that we can use to stem different word. Then, rather than creating this string, so remove text, we just define a function, get sorted stems applied to some text, not defined, sorry, text. Okay. So this should be a slightly more rational program. Given an arbitrary text, hopefully written in English, we call the function getSortedStems that performs all the steps that we have seen up to now. Tokenize, convert into lowercase, take the stems of the words, filter the stems only keeping words and removing punctuations, sort them, and return the list of sorted stems. Of course, we need to check something. For example, if we have two equal words. Oh, actually, I thought that sorted would eliminate double words, but let's see. Well, actually, we have two possible things that we can do. Either, rather than using a list here, we convert it into a set. Okay, so this automatically removes all duplication. Okay, set is another primitive type of in Python that just removes duplicates. But actually, I would prefer to keep a list because I prefer to have them sorted alphabetically. So one possibility, it's not the most efficient one, but it should work. So first we take a set and then we sort it. So that we get a list again, this time without duplicates. Of course, this is using a lot of computer resources in large documents because converting a list into a set and then sorting it, returning a list again, is not the most CPU efficient way to do it. But anyway, it's a important is that we get the result now. Okay, so what I suggest is, after we have filtered the stems, we convert it into a set to remove duplicates and then we sort them. So we remove duplicates and the word hello appears just once. So we can apply the function to two different strings, for example. I don't know, the first may be the same as before. This is into the text. Let's say this is another short text. So we have two texts that are similar to each other. So if you look at the two lists, okay, you see it works. Actually, you see that the Porter algorithm is not the best we can do. For example, here from another, it has removed the part, while it shouldn't have done that. And also from this, it has removed the yes. Anyway, okay, this is what we get from this package. Then I'm sure that there are many refinements that can be found, but at present, let's keep this. Okay, what I would like to do now is, can we compute the Jacquard coefficient of these two sets, of these two lists? So, suppose that we store the two stems into two lists, L1 and L2. How do we compute the Jacquard coefficient? Okay, we need three numbers to do that. The number of elements in the two lists, and we have it. And then we need the number of elements in their intersection. So, let's do it iteratively. For example, we can store the length of L1 and the length of L2. And then, okay, let's just try to find the common elements in the two lists. Remember that the two lists are sorted, so we just need to scan them once in order to find the common items. So the idea is that we use two indices, I1 and I2. And we keep the count of intersections in another variable, let's call it n, initially 0. Then we just do while n1 is less than the number of elements in the first list, and I2 is less than the number of elements in the second list. Just check if the I1 element of L1 is equal to the I2 element of L2, we increase n and we move forward the two indices. Otherwise, actually, I don't remember if we can compare strings with the less than operator. Why? Okay, this seems to work. Okay, so the idea is that we have two lists and we sweep them by moving the index of the list containing the string which comes first in lexicographic order. So that by scanning the two lists we can we count the number of equal items. Of course, the Jacquard coefficient, it's called the JC, is equal to the size of the intersection, which is n, divided by the size of the union. And the size of the union is length of the first list plus length of the second list minus the intersection. Finally, we need to make it a float division, otherwise we get an integer division which will always be 0. And by writing JC, we should get the Jacquard coefficient of the two lists. Okay, so we get a number that represents the similarity of the two phrases here. Okay? I can leave this code here for a while if you need it. Anyway, it should be rather straightforward. Well, actually, what we can do here is take this code and make a function of it. So let's say we define a function jacquard that takes L1 and L2 as parameters. Computes the jacquard coefficient and returns it. Okay, so we defined the two fundamental functions. The one that, given a text, returns the list of stems, of sorted stems, and then a function that, given two lists of stems, computes the jacquard coefficient of the two by computing the size of the intersection. And then we can test it by creating these two lists and calling jacquard of them. Let me see if it works. Okay. Okay, this works as long as we are willing to write our own texts on in the program. Now, the last thing I would like to do is this. Rather than writing our own text, suppose that we want to download two web pages and we want to compare them to get the jacquard index of the two pages. So, let's forget about this. We just keep the NLTK import, the definition of the Porter stemmer, and then the two functions. Now, if we want to download a web page from the internet, we can import URL lib. Okay. This is the package that provides one of the packages that provide access to web pages given URL. We can also write a short function. I don't know. Let's call it download. That given a URL provides the text of the page. What can we do? We just need to create a file f using the URL open function of URL lib, passing as an argument the URL that we want to download. And then f is just a file, so we can assign it to a variable HTML, for example. We read the whole content of the file into the variable HTML. Now we can close F. Of course, this page will be full of HTML tags. I would prefer not to have them. So if possible, we remove all HTML tags because we are only interested in the text of the page. And we can do this with a method of the NLTK package. So we can return clean HTML from the text that we have just downloaded. Okay, so this function opens a URL, reads the whole text into this variable HTML, closes the file, and then removes the HTML tags and returns them. So we can test it, for example, by asking to print the result of the function download to some URL. I don't know, maybe HTTP. Well, let's see the homepage of the course. So let's see if it works. Okay, so this is the web page of the course where all HTML tags have been removed. Okay, we only have the text. So instead of just downloading it, we can get the sorted stems out of this page. So we get the list of stems of all the words that appear in that page. Each just once. We can use this, for example, to compare two tests and see how similar they are to each other. For example, we can check a couple of Wikipedia pages. So, for example, let's see, if we go to two pages that contain something related to our work, to this course. For example, I don't know. This is the page about stemming, and the page about okay, let's see, the vector space model. or maybe even more similar, probably, the Wikipedia page on PageRank and the Wikipedia page on hits. Suppose that we want to compare them. So what I want to do is download the Wikipedia PageRank page. Let's call it. So this is PageRank will contain the text of that Wikipedia page. Then we can do the same for the hits algorithm. Oh, as before, of course, we are mainly interested in the list of sorted stems of the two. So that we can print the Jacquard coefficient of the two stem lists. What I expect is, well, it's a bit higher than I thought. Why is it so high? Oh, no, okay. We had a problem. Wikipedia would not provide the page directly to... Okay, that's not a problem. Oh, no, the problem was that I could not pass the proxy, actually. I was blocked by screen. I see somewhere. I see. Well, okay. I can just take the two pages. Okay, so now we have an internal copy. Here, okay, without pictures and style sheets and so on. And the other is grids. Okay. Okay, now the Jacquard coefficient is much more realistic. So if you look at these two HTML versions, you get a Jacquard coefficient of 0.26. What can be interesting is, let's go to a completely different page. Maybe again from Wikipedia. So let's just go to today's featured article, okay, on Titan, the moon of Saturn. Of course, this page is completely unrelated. We can expect it to have much less words in common with the other two. So let me just move this page. Okay, so now we have the page titan.html. So we can see, we can compare the three Jacquard coefficients. Let's see what happens. Okay. So you can see that the Jacquard coefficient between PageRank and its is higher than the two Jacquard coefficients between either of the two pages and the page about Titan. Of course, we still have many common words, because being this a Wikipedia page, it has a lot of index words around the copyright notice. In particular, we haven't eliminated any stop words here. So even the
is considered a common word between the documents. So here, actually, in the two Jacquard coefficients below, we have a lot of noise, okay, of things that should not be there. So other steps that we may consider in the next weeks can be, okay, looking at the overall vocabulary and removing all words that appear too often by looking at their inverse document frequency, for example, and so on. Okay, I think this is more or less all that I wanted to say today.
I suppose yesterday you talked about Jacquard question. So if it's less, this means they have a lot of words in common.
No, if it's less, it means that they have less words in common.
Okay, so the first experiment was like 0.9, so it's almost 1. It's in terms of probabilities or?
Oh, it's between 0 and 1, in fact, you can also interpret it as a probability because it means it's the probability of, well, if you select a word that it appears in both documents.
Probably it's 1.
Yes, the probability, so that coefficient is 1 when the two documents contain exactly the same words.
Yes.
0 if there have no common words. So in this case, in any case, higher means that the two documents are more similar. So the first refers to page rank and hits, while the other two refer to page rank and title, or hits and title. Of course, if you compare them with a page that comes from a completely different context, well, not really a completely different context because the course page contains a lot of words related to Wikipedia, hits, PageRank, and so on. But again, the similarity has dropped at least in this case. Anyway, of course, it's important to also perform some form of stop word removal when we do that. So removing all words that are too common. Okay, so I think that's all.